Right now, 100 miles of California's coastline is being swallowed alive. Highway 1, the most iconic road in America, is collapsing into the Pacific Ocean in multiple locations along a 60-mile corridor. 40-foot walls of mud and debris are burying homes, crushing vehicles, and erasing entire landscapes in a matter of hours. Big Sur is disappearing. Satellite imagery confirms what ground teams feared most. Entire mountainsides are creeping downhill at 3 to 5 inches per hour, their soil so saturated it has begun to behave like liquid. Tourists are trapped between collapse zones with no road in or out, and helicopter rescues are failing in 90-mile-per-hour winds. Is Big Sur facing total geological collapse? How did a coastline celebrated for its beauty become one of the most dangerous places on the continent? And if the mountains themselves are moving, who can possibly stop them? The first warning came from ground sensors embedded near Rocky Creek Bridge. Instruments registered sudden lateral displacement in the roadbed, the kind of shift that precedes catastrophic failure. Within hours, a section of Highway 1 sheared away from the cliff face and tumbled into the Pacific, taking guardrails, asphalt, and the earth beneath them into churning gray water. Emergency closures went up immediately, but the road was already gone. Motorists caught between collapse zones had nowhere to turn. To the south, a massive failure reopened near the Mud Creek site, a zone that UGSH had been monitoring since 6 million cubic yards of earth buried the highway there in 2017. To the north, the pavement crumbled at ragged Point and Plaskett Creek in rapid succession. This was not a single landslide, it was a chain reaction. Within 12 hours, the full corridor from Cambria to Carmel was sealed shut. 47 vehicles sat abandoned on fractured pavement, their occupants among more than 180 people stranded in a landscape that was actively dissolving beneath their feet. Caltrans declared a full closure, with no entry, no exit, and no timeline for repair. But the collapse had only just begun. 3 atmospheric rivers bore down on the Central California coast in rapid succession, a pattern that climate scientists at Scripps Institution of Oceanography describe as an AR family, exceedingly rare in its intensity. Continuous bands of moisture stretched thousands of miles from the tropical Pacific to the Santa Lucia Mountains, delivering rainfall that at its peak could have exceeded 6 inches per hour in the steepest terrain. NOAA's integrated water vapor transport readings approached 1,600 kilograms per meter per second, levels rarely observed outside of the most extreme atmospheric river events on record. An average atmospheric river carries moisture roughly equivalent to the flow at the mouth of the Mississippi River, but exceptionally strong ones can transport up to 15 times that amount. Based on what forecasters could measure, these stacked moisture plumes were delivering water volumes that no operational climate model had projected for decades to come. The conditions were decades ahead of schedule.
The mountains could not absorb it. The soil could not hold it. The water had nowhere to go but through. Near the Nepenthe restaurant, a beloved landmark perched high on the cliffs above the sea, 40-foot debris flows roared downhill with the sound of grinding boulders and snapping timber. The access road vanished under a wall of mud, rock, and shattered redwood. The smell of wet earth and torn vegetation hung thick in the saturated air. 500,000 cubic yards of earth moved in a single event. In the Ventana wilderness, satellite imagery captured entire ridgelines in motion, their surfaces sliding in sheets toward the valleys below. The terrain rippled and buckled as subsurface water pressure exceeded the shear strength of slopes that had stood for centuries. What happened next stunned even the geologists. At Big Sur State Park, millions of cubic yards of saturated soil and fractured rock cascaded through the canyon in successive waves. Trails, campgrounds, and access roads disappeared beneath layers of debris so deep the original terrain was unrecognizable. 15 major mudslide events struck within 4 hours. The air was choked with the smell of pulverized granite and rotting organic matter. Landscapes that had taken millennia to form were erased overnight. And still, the rain kept falling. Highway 1 was severed in so many places that engineers stopped counting individual breaks and began mapping entire zones of failure. Cell towers toppled along the ridgeline, cutting communications across the region. 85,000 customers lost power as transmission lines snapped under the weight of collapsing hillsides dragging their footings down slope. The cascade spread faster than anyone anticipated. Water treatment plants switched to emergency backup systems with limited fuel reserves. Sewage containment became uncertain as lift stations lost electricity. Natural gas lines required manual inspection before any service could resume, a process that demands stable ground, which no longer existed anywhere in the corridor. Emergency supply delivery shifted entirely to helicopters, multiplying transport costs by a factor of 10. The infrastructure did not fail in one place, it failed everywhere, all at once. USGS field teams measuring soil conditions across the Santa Lucia Range reported saturation levels far exceeding anything in their monitoring history, with some readings suggesting values 400% above normal thresholds. Every cubic meter of that waterlogged earth now weighed roughly 2 metric tons. Across the coastal slopes, billions of tons of material pressed downward on surfaces that had already lost the friction to hold. The mountains were becoming liquid. Researchers at UC Berkeley's Seismological Laboratory, which monitors seismic activity across California, detected thousands of tiny tremors along the corridor, each marking a fracture propagating through the substrate beneath the road. These were not earthquakes in the traditional sense. They were the sound of the earth tearing itself apart under its own weight, the kind of slow-motion rupture that, based on what we know of slope failure mechanics, suggests deep structural compromise. Satellite-based INSAR confirmed what the seismic data suggested. Entire hillsides were creeping toward the ocean at measurable, accelerating rates. But the numbers told only part of the story. The 2017 Mud Creek landslide had been the largest in Big Sur's recorded history, dumping 6 million cubic yards of rock and soil into the Pacific and burying Highway 1 under 65 feet of debris. That single event cost $54 million and took more than a year to repair. USGS scientists now reported that the current volumes of displaced material were exceeding that benchmark in multiple locations simultaneously.
15 additional high-risk sections of Highway 1 were flagged for imminent failure. No one had ever seen destruction at this scale along the corridor, and the human cost was just beginning to surface. In a rented cabin 2 miles south of the Nepenthe Overlook, the Martinez family woke to the sound of trees snapping outside their window. The floor vibrated with a low, continuous tremor, not sharp like an earthquake, but rolling like the ground itself was breathing. By the time they reached the front door, a river of brown water and gravel had swallowed the driveway, and their rental car sat buried to the door handles in mud. They climbed to the second floor and waited. For 3 days, the family rationed bottled water and canned food while the rain hammered the roof and the hillside above them shed debris in slow, grinding waves. The children slept in the hallway, away from the windows, because the family feared the glass would not survive another impact from tumbling rock. When a helicopter finally reached them on the 4th morning, the pilot hovered at an angle over the collapsed access road, buffeted by wind shear that made a stable landing impossible. A volunteer firefighter on the ground guided them to a clearing through ankle-deep mud. "We have never had to pull this many people out of terrain this unstable," he said, his voice raw from shouting over the rotor wash. The story repeated across the coast. Luxury resorts along the ridgeline, Post Ranch Inn, Ventana Big Sur, the Esalen Institute, evacuated guests into a storm that offered no safe direction of travel. Shelters in Monterey and Carmel filled beyond capacity. Elderly residents who had lived along the coast for 40 years lost everything they owned to mud that filled their ground floors in minutes. Local businesses faced ruin, their inventory destroyed, and their customers unable to reach them. The economic toll staggered even seasoned disaster analysts. The 2017 Mud Creek repair had cost $54 million for a single slide. If current damage patterns held across all affected zones, early estimates suggested restoration costs could exceed $500 million, with some engineers warning the total could climb into the billions. Big Sur's tourism industry, which in a typical year draws 5 million visitors and generates over $1 billion in economic activity, ground to a complete halt. Insurance claims from homeowners, businesses, and infrastructure operators were projected to surpass $3 billion. A federal disaster declaration unlocked FEMA resources, but the logistical reality was grim. Agricultural supply chains collapsed as farms lost their only transport link, and based on what previous closures had shown, crops left without road access could rot in fields within days. The cost was not just financial, it was existential. Offshore, the ecological toll mounted in silence. Millions of cubic yards of sediment poured into the Monterey Bay National Marine Sanctuary, one of the most biologically productive coastal ecosystems in the Pacific. Based on NOAA's own research into past landslide inputs, turbidity plumes of this scale could smother kelp forests that anchor the nearshore food web. Fish populations, based on sanctuary monitoring data from prior events, would likely scatter from disrupted habitat. Endangered black abalone, sea otters, and nesting seabirds all depend on the nearshore zones now receiving unprecedented terrestrial debris. USGS studies had long established that large landslides deliver sediment equivalent to over 2,700 dump truck loads per mile of coastline annually, and this event appeared to dwarf all historical baselines. The sanctuary had never faced an input of this magnitude. Forecasters identified additional atmospheric rivers forming over the Pacific, bearing down on the same battered coastline with 10 to 20 more inches of rainfall projected within the week. The hillsides had already exceeded their saturation capacity. There was physically nowhere for the water to go except downhill through whatever remained standing. 5,000 additional residents received evacuation orders. Many refused to leave. Emergency personnel, already stretched beyond endurance, faced an impossible calculus. Resources sat trapped behind collapse zones, and fuel reserves dwindled with every passing hour.
Crews who had worked 72-hour shifts showed signs of dangerous exhaustion. The next disaster was approaching before the current one had ended, and the geology offered no pause. No one could promise the ground would hold. Highway 1 has collapsed before, more than 55 times since its completion in 1937, almost entirely due to landslides. In 1983, severe winter storms closed sections for months, and the 1998 El Niño season triggered failures that reshaped entire stretches of coastline. The 2017 Mud Creek failure was described by USGS as catastrophic. In 2024, the Regent Slide, originating 450 feet above the roadway, compounded a closure that had begun with Paul's Slide in January 2023. Together, they blocked full coastal access for nearly 3 years, the longest continuous closure in Highway 1's history. The road itself, built between 1919 and 1937 with prison labor and dynamite, was never designed for what the 21st century would deliver. The pattern is unmistakable: build, collapse, rebuild, collapse again. Some engineers now argue that Highway 1 through Big Sur should be permanently abandoned in its most vulnerable sections. Others have floated proposals for tunnel systems that could cost upward of $10 billion, bypassing the worst geology entirely. A third camp advocates seasonal access only, reopening each spring and accepting closure every winter. Each option confronts the same fundamental question: does human infrastructure belong on terrain that geology is actively reclaiming? The Earth does not negotiate. Every road, bridge, and power line along this coast was engineered for a 20th century climate. The storms arriving now belong to a different era entirely. Atmospheric rivers are intensifying as Pacific sea surface temperatures climb to record levels. The jet stream is destabilizing, steering moisture bands into narrow, devastating corridors that hammer the same geography for days.
Climate models built a decade ago underestimated the acceleration. What scientists projected for mid-century appears, based on current observations, to be unfolding now in real time across a coastline that 5 million people visit every year. This is not unique to California. Across the Northern Hemisphere, infrastructure designed for a stable climate is meeting a world that no longer provides one. Europe floods, the Arctic warms several times faster than the global average, and along the Big Sur coast, mountains slide into the sea on a timescale that no engineer ever planned for. The implications reach far beyond one highway. Tonight, Highway 1 remains severed across multiple zones. Crews work in rotating shifts, patching what they can, knowing another atmospheric river is already spinning into formation over the open Pacific. Recovery timelines are measured in years, and some sections may never reopen. The financial burden compounds with every hour of rainfall. The mountains of Big Sur are still moving, the rain is still falling, and the ocean, patient and indifferent, continues to accept whatever the land surrenders. Scientists know that the geology of this coastline is inherently unstable, a collision of tectonic forces, ancient landslide deposits, and fractured Franciscan complex rock that has been sliding toward the sea for millions of years. What remains unknown is whether this crisis represents a temporary acceleration or the beginning of a permanent transformation, one in which the most beautiful stretch of road in America ceases to exist. If the ground itself is rejecting every structure we place upon it, what happens when we finally run out of road?